Thank you for joining me. My name is Joshua Stuckner. Today I'm going to talk about some of the work my colleagues and I have been doing at NASA Glenn Research Center to enable ultra-efficient multiscale modeling by using a neural network as a fast and accurate surrogate to replace a physics-based microscale model. Modeling and virtual experimentation can speed up innovation and save money by allowing us to test designs without performing expensive physical experiments. Multiscale modeling is often required to capture relevant physical effects that span broad time and spatial scales. Multiscale models must strike a balance between speed and accuracy. In order to accurately model larger simulations or perform design optimization, we need more efficient multiscale models. Our goal is to build ultra-efficient multiscale models that are fast without sacrificing accuracy. In this work, we trained a neural network as an accurate and computationally efficient surrogate for a microscale model. We then embedded the machine learning surrogate into a macroscale model, replacing the original physics-based microscale model. In doing so, we were able to vastly increase the computational speed without sacrificing accuracy. So our goal is to model the physical response of a composite material to external loading. So here we have a composite laminate, which is composed of several plies arranged in a specified orientation. And each ply is composed of a fiber and matrix material. So what we're going to do is model the macroscale response of this composite using classical lamination theory, where we're going to apply a global strain increment and then using the homogenized stiffness of each ply, we're going to calculate the global stress at that increment that the material, the composite is feeling, and we're going to localize this strain down to the individual plies. Then we're going to pass those local strain as well as the material properties in the current damage state to the microscale model to calculate the next homogenized stiffness. So at every time step of strain increment and on every ply, at least one or two subcells per ply, we need to do a calculation of the microscale response of the material. Um, so this microscale generalized method of cells is going to take the local strain increment, the material properties of the fiber and matrix, and here we're using isotropic materials, and the current damage state. And it's going to calculate the homogenized stiffness, which is what the stiffness of this material would be if it was, or this cell would be if it was all one material, and any updated damage. So this microscale model can start to get expensive when we use a high fidelity representative unit cell to represent the microstructure of the fiber. So we need a ton of subcells if we want to accurately get a circular fiber, but it requires a lot of calculations, and those calculations especially add up since we have to evaluate the microscale model numerous times. We have to evaluate it every single time step for each individual ply, sometimes multiple times per ply if we have multiple integration points. And so if we want to gain computational efficiency, what we can do is replace this microscale model with a neural network surrogate. Now, neural networks are seen as very general nonlinear approximators. So what we can do is use data generated from GMC as training data to teach the neural network how to mimic GMC. So once we've generated enough training data, we can have a highly accurate surrogate to replace as a stand-in for GMC. This is a schematic of our neural network surrogate model, which we'll use as to replace GMC. So on the left, here we have the inputs to our model, which include the strain tensor, which is the localized strain coming from the macroscale model, CLT. And we also have the material properties of the fiber and matrix, which we'll input into the surrogate model. And on the right, we're going to output the homogenized stiffness tensor, which relates the stress to the strain according to Hooke's law. And again, this is the homogenized stiffness of the entire ply or integration point of both fiber and matrix. After the input layer, we have two fully connected dense layers composed of many neurons. Each neuron calculates a fairly simple calculation, which is just the weighted sum of the previous output plus a bias, and then we run it through an nonlinear activation function. Now, these weights are the trainable parameters that the model learns from the training data, or in this case, the GMC model. So you may be wondering where damage is input into this model and where it's output. So the nice thing about the LSTM long short-term memory layer of the neural network is that It actually remembers the previous input. So this is the LSTM cell unrolled through time. So we'll get an initial input and it'll give us an output, but it'll also remember what happened and then send it to the next time step. So at the next strain increment, it will remember if there was damage in the previous increment. It can remember loading history and matrix or fiber failure, and then use that when it's computing the output homogenized stiffness. Here are the results of the computational efficiency of the different microscale models embedded within the macroscale model. We compared GMC, a higher fidelity version of GMC, and the machine learning surrogate. We ran a multiscale simulation for 200 time steps. When using a low fidelity representative unit cell, or RUC, to model the plies, GMC and HFGMC were actually a little bit faster. However, when we went to a much higher fidelity representation of the fiber, the machine learning model was significantly faster, with about a 30 times faster with GMC and about 145 times faster computational speed using HFGMC. Now, I do want to point out that there was a jumping technique that was used for GMC and HFGMC where they didn't actually calculate the microscale model at every iteration, but instead, by assuming elastic behavior, they could calculate when the next damage would occur and skip to that increment in the macroscale model and only calculate the microscale at those points. And the machine learning surrogate did not do that and calculated the entire stress strain curve and the homogenization at every time step. When we didn't use that jumping technique, GMC and HFGMC here were on the order of about 10 seconds and on the order of about 1,000 seconds here, even more for HFGMC, of course. And this so even with low fidelity, if we were to use a non-elastic constituent damage model, we would expect the machine learning surrogate, it would still be at this exact same time, but GMC and HFGMC wouldn't be able to use that jumping technique, it wouldn't be slower. But in any case, we have significantly faster speed up in the high fidelity models or high fidelity representative unit cell. And we gain that computational speed with very little loss of accuracy. So here's some accurate results showing a simulation with these material properties on an 8-ply laminate and a 2x2 representative unit cell. And we used this laminate stacking configuration. Now these material properties and these angles were not in the training data that the machine learning surrogate was trained on. So the model was able to generalize to other material properties and other angles. And so here are the results. We have the global stress strain curve of the entire laminate reported by CLT when it was embedded with GMC versus the surrogate. And the results are right on top of each other, basically. And here's the homogenized stiffness values for all of the at each time step that the microscale model reported with the machine learning surrogate in yellow and GMC in blue. And overall, the accuracy when run for a bunch of different laminates, a bunch of different simulations, on average, the mean absolute error for the global stress for the stress strain curve, the difference was about 8.6 megapascals with this R-squared value, and the homogenized stiffness value was at about 0.4 megapascals. And in the case of the high fidelity microscale representation, where we got the significant speed up, we got very similar accuracy, still highly accurate. Here's the representation of the global stress strain curve of the macroscale. As you can see, it's a little bit finer. The curve is a little bit finer here, but we have still highly accurate results. The curve's a little bit finer here as the individual plies are failing, stiffness is failing a little bit at a time, but we still get highly accurate results. Overall, it was slightly less accurate with the global stress being about 10.5 megapascals, mean absolute error across a bunch of different laminates, and the homogenized stiffness was about 2.4 megapascals, mean absolute error. So all in all, highly accurate results, fantastic speed up. To conclude, we successfully trained machine learning models as efficient, accurate surrogates to GMC and HFGMC. In the case of HFGMC with a high fidelity microstructure, we achieved 145 times speed increase by using the surrogate model. And we were able to predict the homogenized stiffness with a mean absolute error of 2.4 megapascals, and even better in the case of the low fidelity microstructure. In the future, we plan to use these surrogates to model much larger problems and perform design optimization. Thank you very much for your interest in my talk.